Cool. Can you guys see the paper?
Yes.
Okay. So before we start on this paper, I wanted to give you a reason why I chose it. So I've been interested in not like the research that I do, but I've been interested in this idea of can we train a model to train itself, or and more likely, can we pre-train a model and then use that model to do continual learning on itself? So could we take one of our language models today and in some way train it to continuously like absorb information from the internet such that it becomes more and more capable and more intelligent? I think that's a really interesting field of research. That's really in its, in my opinion, in its baby steps right now, because it's pulling on, it would mean that we would, it's like kind of continual learning, but the problem is that that's never been a really widely studied problem. I mean, there's people who are experts on it, but I mean, it's not like, I don't know, computer vision classification tasks where there's like so many more people who are an expert on it. So it's an area that's really just, I think, started to take off because now we have models where maybe it's possible, whereas before it was more of like a theoretical exercise, or a conceptual exercise is probably the better word. And so I've been interested in that, and we talked to our advisor, Yaron Gall, and he's like, oh, we have a paper that's kind of related to that topic, and it's this paper. And so I was like, you know what, I'll present this paper. And this paper, it doesn't exactly address the topic that I just told you about, but it does address a component of it, which is the basis for this paper is we have like stable diffusion models, as they say in the abstract here, which are great for generating images from text. And then we all of a sudden also have all these amazing language models, which are great at generating text for a wide variety of tasks. And people are using these things in our world a lot. So, and not only are they using it, but they're publishing those results on the internet. I mean, you have examples of like people using generated images to create Instagram accounts, or people writing articles using ChatGPT and just publishing them. And so one really big element that has caused the huge, like amazing performance that we see in these models is the fact that they're trained on the internet. And so if you are training these models on the internet, and like each new iteration is trained on like a larger like the internet as it is up to a certain date, that means that over time, like probably a larger and larger quantity of the data on the internet will be generated by these models. So the question they're trying to address here is, what impact does training a model on data that's been generated from a predecessor model have, or like a mixture of like the original data and model that's been data that's been generated by another model? Because that's a pretty similar setting to what could happen in the future. I think the only thing about this paper that wouldn't be exactly the same is that like when people are generating content using these models and putting it on the internet, probably they'll be injecting some new information into them. Like, you know, maybe BBC will use ChatGPT to write an article about like a new oil spill that occurs, or some report that comes out of, I don't know, like a government organization. And then they'll be using the model to generate the article, but they won't actually be asking it to fabricate the facts that have come out of the, like, that they've gotten from some real world source. So I think that's the only difference. But I don't know how much. I can see why they don't try to address that element of it here, and I don't know what that means in terms like of the implications of this paper if you take that into account as well. But anyway, so this paper is trying to look at like what happens if the internet becomes filled with generated data from models at different, like, maybe GPT-5 will be generating all the articles from 2025 to 2026, GPT-6 from the year on, and like, so when the internet is populated with all this data. And so the reason why the paper is called The Curse of Recursion is because what they found in some toy examples, but with some logic which I think probably and they show through experiments with more complicated models, but like with some logic that makes sense, is that you get something they call model collapse, which I'll define later. And so this model collapse, well, actually, I'll wait for the definition to just read the definition out exactly. But yeah, it's a really cool paper because it demonstrates with some like really basic examples that this is a problem that we have to take into account. And really the end of it is just like human data is so valuable because, and generating data with these models really probably doesn't add that much, especially as you go towards the limit of doing it over and over again. Okay, long-winded explanation over. So let's start going through it. I'm actually going to wait. I'm not going to do the theory till the end. I was thinking about how to present this, so I'll just go through it, but skip the theoretical part of it, and then we'll go into that at the end. I think it's very interesting, but I want to just go over the simple parts before we dive into the more complicated parts. So one point that they actually make is that in the introduction, which I highlighted, is that we've actually been using machines to like generate text for a while because we've been using them to like correct our spelling and grammar for a long time. So that's one way in which the internet for a long time has already contained some like generated text. But they're saying now that we have large language models, it's going to be even more so. And one interesting thing that they point out is that these models now arguably pass a weaker form of the Turing test in the sense that their output cannot be reliably distinguished from text written by humans. So yeah, these models are hard to distinguish from people in terms of what they write. Just interesting points that I thought I wanted to talk about. I won't go over the rest of the introduction because it will become evident as I go through the definitions. Just two things in terms of related work. One is that they point out that the two most similar settings to what they're studying are catastrophic forgetting and continual learning. And that's when, in continual learning, it's usually defined as this case where you have a model that's trained on a sequence of tasks that are similar to each other, and you have a different data set for each task. And what can easily happen is that the model will forget like what it learned in earlier tasks based on the data in the current task, like if you overfit to the current task, for example. But they point out that this setting is different because like one, our work is more similar to task-free continual learning, which isn't really studied in terms of catastrophic forgetting yet. And they say where data distributions gradually change without the notion of separate tasks. Our work examines a particular scenario in which the changed data distributions arise from the model itself as a result of training in the previous iteration. Okay. And then the other, and they show a good example of, this is an example of catastrophic forgetting. I'm not going to go through it, but you can see just quickly, like you get this really nice explanation in Generation Zero about St. John's Cathedral. And then in the end, it starts talking about jackrabbits. So like, and giving @ signs. So you can see how bad catastrophic forgetting can be. And then the other point that they make is that the other setting in which that is similar to this is called data poisoning, which is when you can like inject a small or maybe large amount of data into a data set to make the model behave in a certain way that wasn't intended by the people who are using that data. I think we did another paper on this recently where we're showing how like you could inject triggers into a model so that it could like lie, or I think the ones that they were using was like inject a trigger into a model where it's like all of a sudden becomes kind of an unsafe model, like being racist or something like that. So that's a similar setting in the sense that like it's where you're injecting data to change the data distribution such that you're able to get these behaviors out of it once it's trained. Just some related work. And so you can see like how these settings are kind of similar, but they really don't touch on the problem that's being touched on here, or like the problem that I was saying, like, that I think is a really cool, interesting research project. Okay, so let's talk about model collapse, because the whole point of this paper is that by training the model on generated data from a previous model, you get model collapse, and model collapse is bad. So what is model collapse? Model collapse, and by the way, they get the term model collapse from the GAN literature, where you have mode collapse, which is that in the way that you train a GAN, one like local minima that's really easy to fall into is one where it just generates like a single example that it memorizes for each class or for the data distribution, because that will always be like, if you can that example will always have a high likelihood because you memorized it and it's probably in the data set. So that's a failure case of GANs, and they're saying we can see something similar, and we're calling it model collapse because it's where the model collapses to a specific distribution of the data. I'll read it here. Model collapse is a degenerative process affecting generations of learned generative models where generated data end up polluting the training set of the next generation. In a way, and they're saying that, and what it like leads them to do is to then misperceive reality. I think I don't know how I feel about that term, because I think it implies consciousness when you say misperceive reality, but basically it's saying that the distribution that it's learning is different than over the data is different than the actual distribution. So when it sees something, its internal like representation of that distribution is telling it something different than than is actually the case. And they say we separate two special cases: early model collapse and late model collapse. So in early model collapse, the model begins losing information about the tails of the distribution. And in late model collapse, model entangles different modes of the original distribution. So basically, like they're saying the model, like all these generative models and in the sequence that you train, they're going to probably like output data from different modes of the distribution, and then they're going to get all mixed up in your overall data set. And this makes the model converge to a distribution that carries little resemblance to the original one, often with very small variance. So this last part is not something they show in the theory, but they do show it in their experiments. And that was the part I was most confused about in a way, because I was like, I feel like there should be some kind of mention of the fact that this wasn't really shown in theory. But anyway, we'll talk about
Peter,
that. Yeah.
Have you heard the term Habsburg AI?
No, I haven't.
Someone just commented that they heard this term in the same context.
Okay, cool.
I'm Googling it now, actually. But basically, it's about training on generated data. And strange things happen when you do that.
Yeah. Maybe one of the people that's written this, because this paper is not super, I mean, it's probably in the last year, but it's not like it wasn't released recently. Maybe they're working with them. That'd be cool. Okay. So they say, note that this process of model collapse is different from catastrophic forgetting in that we are considering multiple models over time in which our models do not forget previously learned data, but rather start misinterpreting what they believe to be real by reinforcing their own beliefs. Basically saying that models, when you train models on data that's generated from previous models, you can start creating an echo chamber, which shifts the data distribution you're trying to learn. So they say this process occurs due to two specific sources of error compounding over generation. So there's two sources of model collapse. Let's look at them. Yeah, I want to do that. So there's two causes of model collapse. One is statistical approximation error, and one is functional approximation error. And there's actually a third one which they don't study, but they mention, which is floating point approximation error, which they argue, I think it's similar to functional approximation error, which is that like the way that we store floating point numbers on our computers, like the way that they're stored, there's like when you load one, there's always an error with respect to the previous one. So for example, in PyTorch, I know that you can only expect a float to be correct up to 6 decimal points or something like that. And funny enough that especially when you're doing these, you have these like huge models, these floating point errors can have some impact on things. But anyway, so they say in this paper that the primary source of like model collapse is statistical approximation error. And they say, which arises due to the number of samples being finite and disappears as the numbers of samples tends to infinity. This occurs due to a non-zero probability that information can get lost at every step of resampling. So I was like quite confused actually what they meant by information getting lost, but they have a pretty good example of it. So I'll go through that example. It's actually touching on the theory, which I said I was going to do last, but I think this visual example is a good way to talk about statistical approximation error. So say that these are two distributions. Each of them, it says, okay, so the one here in the middle, this one, real distribution 2, it's a Gaussian mixture with a mean of -4 and 4 and variances of 1. And then the distribution on real distribution 1 is a Gaussian mixture, is not that, but it's like it's a distribution that's similar but has fatter tails. So maybe it has the same mean but has fatter tails. So like a t distribution or something, a mixture of t distributions. And they point out that say you take like 100 samples of both of these, the tail events in the in the distributions are much less likely to be sampled than the mean or something near the mean. So you could sample like 100 samples from both of them and then fit a new distribution to those, and you could very likely get something that looks like this, which is basically the same for both. So basically through the sampling process and refitting process, you've lost information about the tails of both distributions, because that information about the tails was lost because those low probability events never were sampled. And so you get like a distribution that has a higher concentration around the mean. So that's what they mean by statistical approximation error. And that's why if you have an infinite number of samples, then it goes away. But to me, this being an issue makes a lot of sense, just because, like, for one thing, the way that we generate text with these language models tends to be like either greedy decoding or some kind of greedy generation, or some kind of random generation that puts an emphasis on high probability sequences. So you could totally see how this type of statistical approximation error could happen in real life, in my opinion. And then the second type of approximation error is functional approximation error. So one thing that we always have to take into account in machine learning is that our models are trying to model some underlying function, but they're parameterized models which may not, either they may be more expressive or less expressive. They might not be expressive enough to approximate that distribution, or they may be too expressive and like basically learn something that's similar but not the same. The example they give for the too expressive is that, or they have it here. A simple example of this error is if we try to fit a mixture of two Gaussians with a single Gaussian. Even with perfect information, model errors will be inevitable. So basically, if you assume that your model is a mixture of two Gaussians when it's actually a Gaussian, the fitting process, maybe the maximum likelihood estimate of the two Gaussians will be different. They won't converge on the same Gaussian, essentially. They won't converge to have the same parameters that are the correct parameters. So here too, this can introduce errors in your in the learned data distribution, which can then propagate and create model collapse. Oh, and one I highlighted this in red because I was like, I want to make sure to say this, that so one thing that the example I showed you over here with like statistical approximation error, if we look back at this plot, excuse me, is that we lose the tails of our distribution. So it's like all the data, all the mass is concentrated around these means. But one interesting element that we see in neural networks is that they can introduce non-zero likelihood outside of the support of the distribution, of the original distribution. So, and they show this empirically. It's just like, so our neural networks, when we like ask them to extrapolate, can put like very high likelihood on like events outside of the support of the distribution. So that's something to take into account. I think it partially makes sense in terms of like, I think we know that models are, we hope that models are less certain when they haven't seen something before, but that lack of certainty tends to mean that the output of our model, like the uncertainty, puts a higher likelihood on a lot of events which may not actually be possible. They also point out here, again, like just the small things, and it's important to note that in the absence of statistical error, functional approximation error only occurs at the first generation, which makes a lot of sense. Like basically, if you have a model that cannot learn the original distribution, but can learn a certain approximation of it, in the first generation, it will learn that approximation, and all the models after, assuming they're the same, will also be able to learn that same approximation. So you won't have this functional approximation error. Okay, so again, model collapse is bad. It makes you learn, it discards your tails, and it also makes you learn a differing distribution than the one that you are hoping to learn, and it's caused by statistical approximation error and functional approximation error. Okay. Here is the theory, which we'll probably spend we'll probably spend a good amount of time on, but I'm going to skip it just for now, so that I can show you the results. Okay, so they use two toy examples. One is a Gaussian mixture model, and one is a VAE, and I think I can just show you all of this best through the images that they have. So they're testing their theory, and in all the model experiments, the way it works is that you have in all of these experiments, you have your real. The way it works is if you look all the way to the left, you have your real distribution. You get a finite number of samples from it. You train a model on that distribution, and then you resample from that distribution. and then you use that to train the next model. So here there's actually, in these experiments, there's no data from the original distribution in subsequent iterations, which is unrealistic in terms of like the real setting that they're going after, but I think it's good for making the point that they're trying to make. So like if you look at iteration 0, it looks pretty close to the real data distribution. That's the second to the second most to the left. And then by iteration 50, we're seeing something quite weird. And then by iteration 100, it flips, but again, it's weird. And if you go all the way to iteration 2000, you can see that it's converged on this this very small set of the distribution is converged on these very small set of points. So it's like there's very little variance. You can see that they're all near one point, and it's just like converged. So
I might have totally missed it. So there's nothing of the original data is re-injected. It's just the newly generated data from
the model.
Yeah, I wonder whether that. I guess it's about the relative size, right? You would expect the original data to sort of pull it back a little bit, no?
Yeah, so they do some experiments, which I'll show after this, where they do inject some data. But yeah, I would expect the same thing.
Gotcha. Thank you.
And then they do the same thing with in an image generation task with a variational autoencoder. So you can see that like these are where they're trying to generate digits on the MNIST data set. So you can see like digits generated by the original model at iteration 0, and by the end, they're just like these blurry zeros or like combinations of things. So you're seeing again the same, like the fact that they all look similar means small variance, and the fact that they're all similar also means like converging on a mean. And they're actually able to, they see the same thing in the latent space of the autoencoder. So like the autoencoder also learns to output like increasingly certain Gaussian distribution, the encoder element of it, as the generations increase. And then with language models, they say like we can't like pre-train a language model and then generate like the data the size of the internet and then retrain it over and over again, because I don't know, we're not Facebook. So instead they focus on a fine-tuning task, which is excuse me, they fine-tune a model on Wikitext2, the Wikitext2 data set, and then they generate data from that data set, from the model that was trained on that data set, and then they retrain it. And they have two cases here. So the way that they're figuring out how good their model is I guess they're giving it like 64 tokens from that data set, so from like a snippet of that data set, and saying generate the next 64. And they use perplexity, which is a measure of like text correctness, as a way of seeing how good it is. And so they what they do is like you can see after many iterations. So in the, on one side over here in A, no data is preserved, which means that none of the original data is kept in the data set when you're training on subsequent iterations. So for example, in the first, and by the way, for perplexity, lower is better. So it's like in the first iteration, you get a perplexity of 35, and then it shoots up to 60 in the first iteration, and then it converges down to a much higher point than the best one, which was the original one. So you can see that like without any original data, you're seeing you get quite a decrease in performance from what you were hoping. And then but what they do in the second experiment is they take 10% of the data from the original data set and like randomly sample it and inject it in with the generated data. And you can see that the difference in performance, again, you have this spike after the first one that converges down again. But you see a much smaller difference in performance. I was actually hoping there would be an explanation of why there's this spike from 0 to 1. Like, why is the biggest decrease in performance here? And then it converges. But instead, they just point out that this experiment is more to show that when you do use generated data, you get a decrease in performance, like in this recursive fashion of training off of the data of the previous model. But it can be mitigated quite well adding some data in from the original data set. Let's see. And they do say that, oh, okay, last set of results before we go into the theory, which is, so again, we have A and B. We have models trained on the same data set, Wikitext2. A is where each generation has data that's been it's been generated only from the previous generation, and then over here, 10% of the data from the original data set is put in. And what they're what they're doing is they're showing like the probability of the based on the model versus the perplexity of the data point. And what the big things that they're showing you here are like there's definitely like a large distribution shift towards data points that have a low perplexity with respect to the original data set, which is most closely approximated by generation 0. But also you can see that they have much longer tails, like the subsequent generations than the original one. It's a little bit hard to see. I wish they had actually put the blue one more prominently so you could compare it, but they just say it in the text as well, that like we see as the generations gets larger that we have much larger tails, which is, I guess, what you would call late model collapse, because they say in early model collapse you forget your tails. But anyway, over here in B, when you inject data, you see a much smaller difference between like the original data set and the ones that are learned. So Arvid, you're right. It seems like injecting data from the original data set helps pull it back. Okay. So we've looked at, before I go into the theory, so the results are just that when you train these models, they actually show two different things, really, if you think about it. Like the first two experiments show that you like collapse on a very small subset of the data with a very small variance, which doesn't reflect the original data distribution. And then over here, they're saying like, okay, with these language models, we're seeing like a distribution shift. So we're not seeing that it's collapsing into a specific small set of the data with small variance. We're actually seeing like high variance, and also that the model shifts its data distribution from the real underlying data distribution, which isn't great. Just pointing that out. Okay, now let's talk about the theory. And I'm gonna stop in 18 minutes and ask if anyone has questions, or maybe even less. The reason why I'm choosing to do this here like last is because it's quite complicated depending on your background. And so like I just happened to be reading some stuff about statistics recently that helped me to understand this stuff. But depending on your background and how recent that is, it might be hard for you to just go through it. So they define this setting as a stochastic process, which makes sense, where the variable that is evolving over time, it's xi, and that's the data set. It's a random variable representing data, or like, and its distribution is the data distribution. So x could be like what cats look like, and images of cats, something like that. And so at each time step, where time step is denoted by, the superscript I, you have a random variable denoting the data set. I don't know how to put it. Let's say a random variable for the data, and it has a corresponding data set di, and then the superscript j denotes like an example in that data set, so 1 to mi. So at each step, di contains at least 2 points. It's not super important, but I guess it's a little bit important. Is it? Yeah, it is. It is important that it's greater than 1. But it doesn't have to be. Yeah, it is important. Okay, for the math. And then we've described all that. And then another element of it, as at each time step, you're going to train an approximation of the data set distribution. So the original data distribution at time step I is called PI. And then the data set distribution at PI plus 1, P theta, is P theta I plus 1, sorry. So no, I didn't say that right. At each time step, there's a data distribution PI, and then we approximate that. We're trying to learn that for the next step based on the current step. So the approximated distribution at time I plus 1 is like a model trained on the data set at time I. And so this model might be able to perfectly learn the distribution that it's at time I, or it might have to approximate it. That's why they introduced this step instead of just keeping PI equals PI plus 1 because of that. And then, let's see. The way it works is that they define their setting as we resample the data set PI plus 1 from the distribution. And so PI plus 1 is equal to A plus the functional approximation plus beta, the actual distribution on the previous time step, and then the original data distribution P naught. And one thing that all of their theory is based on, they're saying alpha and gamma being 0. I actually think this is incorrect. I really think this is incorrect, because if alpha and gamma are 0, then PI plus 1 equals PI, which means that the PI equals P0. PI plus 1, because if you just do if you just think through it. So I think what they meant to say here is that beta and gamma are equal to 0, and alpha is equal to 1, because in all their settings, they're just resampling from the model that they've trained. So yeah, I think this is a mistake in the paper.
So
Otherwise,
what's the difference between PI and P theta I?
So yeah, good question. P theta I plus 1 it's a model that's been trained on the data set from the previous time step.
Okay.
So it's PI, whereas PI is a distribution over the data of the previous time step. So they would be the same if the model that was trained could perfectly describe the distribution. So PI would equal P theta I plus 1 if it was perfect, but there might be a functional approximation error.
And PI would be the actual distribution of the generated data, which itself should follow P theta I minus 1.
P theta.
Because it's generated from the previous step.
Yeah.
Thank you. This equation, where does it come from? That is not quite.
So the reason why they show it is because they're trying to show how they generate the next data set, DI plus 1, but it doesn't come from anywhere. It's like fabricated for the setting.
Okay. Good.
Yeah.
So that
I
was
get what
like a static data setup where after each step they still choose how much data is retained from the previous step, how much data is generated from the model of the previous step, and how much is the original data.
Yeah.
Okay, gotcha. Thank you.
I guess to be fair, alpha, now that what you said that alpha and gamma could be 0 if because alpha and gamma could be 0, and then what you're basically saying that makes sense. So this isn't incorrect. Alpha and gamma are 0, which means that you don't have to worry about functional approximation errors. And so the only errors that could occur in this theoretical setting are from statistical approximation errors, which, if we go back here, was the primary cause, according to them, of model collapse.
Of course, alpha doesn't seem to be necessarily constant, right? So there seems to be like a time dependency. So you could indeed have that pi is unequal p0, just because, if alpha always would be 0, then pi must be p0. But if as long as the time dependence, right, pi could accrue some level of approximation error.
Well, yeah, true. But since you're resampling at every step, if the resampling process introduces errors, pi could not equal p0, even if there's even in the case that they're talking about.
Yeah.
Let's go through the math.
How will you resample from p0? That is a bit odd. But it depends a bit on the sampling method, right? Do you sample if you sample everything, then it is just p0, right?
Yeah. So in this setting, there's a finite number of samples.
Yeah.
And I think that's where the error comes in.
Okay.
So I am actually, should I go over this part? Because I kind of explained this whole thing over here. It's the best way to explain it, in my opinion, like this discrete example, is by looking at this, which is what I already did. There's a little bit more math involved here, but the crux of it is the idea that we talked about, that like in this discrete example, you can see that you'll lose the tails because we can go through the reasoning. So like, say you have a sample size of m. If you consider state I with probability, so state I is one of the discrete states that is possible in the distribution with a probability that's less than 1 over m, then the expected number of examples of that value is equal to less than 1, which means that like in one sampling step, the likelihood of sampling that state would be less than 1. I mean, like there's a non-zero probability that you don't see that state in your new sample set. So when you train your model on that new sample set, you won't consider that state as a possible state because it won't be there. And one thing that's like, I think, quite important to realize, to extend it further, which they don't say explicitly, but actually they kind of do, is that this logic extends to any state, in a sense that, like, say that you are sampling, you do this iterative process an infinite number of times. So you sample your new data distribution, you fit to it, you sample from that fitted distribution, you sample, and so on. Each state in this discrete distribution, there's a non-zero probability that you won't sample it at all, which is equal to, I actually don't think it's equal to 1 minus q like they say here. I think it's equal to like 1 minus q to the power m, which is the number of data points that you sample. But that means that if you do this process for an infinite number of times, the state that it's going to converge on a distribution which only allows for a certain state, because at every single distribution, every time you sample, the argument is like every time you sample, you lose information, and there's a non-zero chance of losing information completely about a state that's possible in the distribution. So the only possible thing that can happen, and if you do this an infinite number of times, is that you'll converge on a distribution where only a single state is possible. So
quick question is that, when we say we lose information about the state, does it mean that the state is available, or that the relative occurrence of that state is diminished, right? So say every time we sample, And let's say we sample the numbers 1 to 100, and
Yeah.
we sample from them and say that it's like semi-Gaussian, it's maximum at 50. If we would train it every now and then, like the first time we sample the number 49 would maybe be sampled only, I don't know, 20 times, which is probably less than it typically would, right? So we wouldn't have to necessarily lose the state completely in order to already get the error in
That's true.
Yeah. No?
Yeah, that's exactly. So it could be that you lose the frequency with which it occurs,
Yeah.
or
and that sort of self-amplifies then, right? Because in the next iteration, it's trained to be lower, and so that the chance for an even lower, like only samples with frequency 10, sort of accelerates, no?
Yeah, exactly. So that they have 2 points, which is like at every step you're going to lose information, and then since there's a non-zero probability of completely not sampling it, at some point this sampling process will converge to a what they call like a Dirac, I think, or delta.
Yeah,
it's Dirac distribution. So yeah, I think this discrete example. Oh man,
I think Dirac doesn't doesn't really exist in a discrete case, right? So it would just say, I suppose
a delta function they call it, I guess.
Yeah, but in a discrete state that doesn't make really sense, right? The delta function essentially is on a continuous space but has like finite mass. So I guess sorry, I think that makes sense because it's a discrete distribution, right? So you could see a discrete distribution as a distribution of delta functions in a weak sense.
Yeah, I've done it before for our stuff because I think it's a useful way of thinking about durations in construction tasks.
Or dequantizing discrete models, right? Where you sort of reverse that, which is similar-ish, I guess.
So I'm gonna. I realize I only have like 4 minutes to go through the Gaussian part, which is too bad. But I'm gonna go through it like super quick and just show you the results. So in the Gaussian in this discrete distribution example, they say that you have a function which can like perfectly describe your data distribution, which is quite easy. And then in the single dimensional Gaussian, they say like, okay, well, what about the case where we have both functional approximation error and sampling error? What happens? So the first part of all of this analysis is ignoring the functional approximation error, and then they introduce it. So let's go through that part first. And I'm not going to go through all of the math here, but basically what they show through all of this stuff is the result down here, which is, so this is for this single Gaussian situation, basically you're trying to learn a model that approximates the mean and variance of a Gaussian, and you're just resampling and learning it. And what they show is that the expected value of the Gaussian at the next time step is equal to like the mean of the original. So the mean is preserved. It's an unbiased estimate, but the variance will grow over time. That's what this is showing here. So n is what is n? N is the number of time steps, and m is like the number of samples in each time step that you take. They're assuming it's constant. So as this goes to infinity, the variance goes to infinity. That's the result that they show here. So they basically show that you can't learn the underlying distribution. I think that they're making the assumption that they're doing, and they're doing an unbiased estimate of the variance, actually. So it's not like a biased estimate of the variance, it's causing it to grow. But anyway, so that's the main result there. And this was something that I was like, this is weird to me because you're telling me that the variance will decrease over time, but now over here, your result is showing that it increases to infinity. We can skip these. And then they introduce, and basically what they show is, I'm sorry I'm going through this so quickly, by the way. I'm happy to talk to anyone who wants to talk about it, if you just email me. But so R over here is the like a measure of the error between the distribution, the original distribution and the distribution at time n+1. And they basically show that it grows over time. That's what they're showing over here. Then they introduce approximation error with these, I think the correct term is innovations, but I guess that depends on what they are. And then they do some more math, and they show again that the approximation error is lower bounded by this, which again will increase towards infinity over time. So the approximation error, essentially, it's showing that, and with when you introduce model approximation errors into it, it also will the error, this expected R, increases towards infinity as this process continues. So yeah, that's the theory behind it. Sorry I have to do that so quickly. I just want to. So anyway, I actually wanted to. Yeah, great. I actually wanted to talk a little bit more about the concept behind this paper, not necessarily the math, which is this idea that we are like populating our information sources with generated data and what impact that will have. In the discussion here, they actually talk about how it's already happened. Like, supposedly there's some people who figured out that you could increase the position of a website on Google search by these, what they call like click content and control farms. And so what ended up happening is that Google was forced to, and that's a way of like shifting the distribution by poisoning it, where Google has put an emphasis on content produced by trustworthy sources, and DuckDuckGo has removed like altogether, I guess, sources that they think are upped by this process. And they also say in their discussion that like low probability events are also vital to understand complex systems, which is, I guess, from Black Swans. And so they're saying that, like, you know, by generating all this data and putting it on the internet, we're making low probability events even less likely based on the data distribution that we're creating. And so I guess for me, the thing that I was thinking when I was reading this last part is that this is a really good point. And I think it also demonstrates how this idea that language models are the solution to everything just isn't the case, because really what we want to use language models for is as experts in different domains. But if we're using language models in this way and we're like trawling the internet to create data for them, then unless we're injecting more expert information and articles from humans into the internet about these things that we want the model to answer questions about, basically it's not going to learn it. In fact, it's going to be worse at learning it over time. So I guess what I'm trying to say is, like, the current paradigm, at least that we're in with how we're training language models, I don't think is going to lead to increasingly better language models. And that's a conclusion that's somewhat supported by this paper. So what do you guys think? Do you think that language models will become super intelligent soon, or something like that?
I don't know. It's so hard to say, but
yeah,
I think it's having just a model in the traditional sense that you train it in the output without any internal thinking, as some of the DeepMind paper tried, right? I think that's going to be impossible.
Mm.
It's still
Yeah,
define intelligent.
That's true. That's true. But you know, Arvind, and what you just said, by forcing internal thinking. We're introducing rules into the way that these models think. And that was a paradigm that for a long time we used in artificial intelligence, but just proved not to be expressive enough. So I'm like,
Yeah.
how do we train a model to do this type of internal thinking without
Yeah.
explicitly asking it to?
I mean, I quite like this DeepMind approach of seeing it as a search space, right? So that the model has to find somehow heuristic rules to navigate that space efficiently. And how do humans do it? We ask questions. At least some do sometimes ask intelligent questions, and that makes people even smarter. So it's just hard to phrase it into a machine learning problem.
True. The other thing I've been wondering recently along those lines is like, we consider ourselves so intelligent with respect to what we used to be, and the rate at which we gather information seems to be increasing. But I'm wondering if that's because we're becoming more intelligent or just because of the knowledge we've already gained. Like, if you put a human alive today back into the Stone Age without the knowledge that they have now, would technology increase at a much faster pace? Like, are we getting more intelligent, or are we just do we have more information acquired? Is like another thing that I've wondered.
Yeah, probably the latter, right?
Yeah.
There's a very nice book by David Deutsch. He's one of the fathers of quantum information theory, and I think it's called The Fabric of Reality. It's a quite cerebral book, but he says one big part of it is that we got better at organizing knowledge. If you think about it in physics terms, how in the past you would have electricity, magnetism, whatnot, but nowadays we know it's essentially all just special relativity applied, and you can sort of derive the form and color of a rainbow from a set of knowledge. So it's this part of where education is important, right? But good education research is essentially a form of how to make more knowledge digestible in such a way that it is compact and can be easily translated. And there is actually recently some a talk about the idea that knowledge also can get lost. That in the past we know from ancient civilizations that they had sometimes very interesting technological advancements, like certain the Romans knew how to do some nanomaterials, for example, like some form of glass that has some very specific properties that has been lost. But and that this of course can happen as well, right? We tend to work in very abstract spaces like coding space, but often we don't understand what's going on under the hood on the say machine level, and the people who came up with that, they are dying because they're getting old, and there's a very real chance that we end up in some state where a lot of that we use stuff that we don't quite understand anymore, and that potentially can lead to problems. Sorry, that is me ranting about something that's not related to the paper at all, but
still interesting.
Yeah.
Cool. Well, I think we'll end there. Oh, there's one more comment. Yeah, I like that point. Okay, I will. Yeah, let's stop here. Thanks everyone for coming today. I hope you enjoyed the talk, and we'll see you there. We'll see you here next week.
See you next time. Bye bye.
Thanks,
Thank you very much for